So I had a couple of questions yesterday, which I did answer, and I also got an email with some more questions. So maybe I will quickly go over that a little bit. So starting with the email regarding the QCD summaries derivation. So the question was, in comparing, I had sent a review, which I should write down. Hold on. The review number in the notes. It's probably the best thing. Yeah. So there's a review. QCD summaries by Colangelo and Pcb. And the number is PH001017. Okay. Now in this review, it seems that, and I confirm that they give a different equation for this Borel transformation from what I give, and that puzzled me a bit because I've always used this equation, and I went back and I found where I found it from, and it was from the supervisor's paper, and so I haven't been able to resolve which one is correct. So I will, for the moment, I'm just going to give you the reference for the paper where I took it from. And it's in all of her papers, actually, on the subject. And this is Patricia Bar and Yelena, and it's a standard reference for these form factors. So I haven't been able to resolve, why this equation is different. And the difference was this factor of 1/m squared in the Borel transformation. So in the end, that doesn't actually make a difference because you apply the Borel transformation to the two sides of the equation, so the 1/m squared cancels. And that's why it's not easy to resolve if it's there or not. Okay, and then the other question was about the validity of the LCS of the expansion about the light cone. So as I said, so there's two conditions for the light cone expansion to be applicable. One is that, as it says here, PB squared minus MB squared should be large and negative. And the other is that MB squared minus Q squared is large and negative. And because, MB squared minus Q squared should be larger than number QCD times MB. So this is also, I would refer you, Anchika, to this paper, the same paper that I cited below from 2004, where they discuss that in more detail. The confusion, I think, is coming from the fact that you were looking up the results for pion form factors, and in that case, there's no MB squared there's no MB squared minus Q squared. There's just Q squared, and therefore Q squared has to be large. But in this case, it's MB squared minus Q squared has to be large, and therefore Q squared should actually be small. Okay. Okay, great. So now let's continue. Unless okay, so no, that was some more questions. The next question that I wanted to answer was referring to why are there 7 independent form factors? And I'm sorry, but I haven't got a satisfactory answer for this paper. I'm pretty sure it's to do with the degrees of freedom when you include the momenta and the polarization vector. There's probably 7 degrees of freedom. I think that's where that comes from, but I'm not 100% sure. But one thing that I encourage you to look at is that one is able to define these form factors in this way. So we write F labeled by some index sigma as a function of q squared is equal to some prefactor sum of the polarization vectors also labeled by sigma. So these are sort of projections with the hadronic matrix element. Okay. And when you work this out, it turns out that you can write down these polarization vectors for the time light, the longitudinal, and the transverse polarizations. And then it turns out that you can define the form factors in this way. And when the form factors are not there, then the result vanishes. So a reference for this would be yeah. And in particular, the appendix, where this is all explained in detail. Okay, great. So, okay, now there was one more question, which is again about the scale cancellation. And I think my answer there is that the scale never perfectly cancels, because even when we do this resummation, we're not including all the possible terms. We can only resum up to a given order, leading log or next to leading log. So there's always going to be scale dependent terms which are missing. And so we're never going to get a perfect scale cancellation, but this implementing this renormalization group running and resummation is a way of improving the scale dependence. Okay, good. So does anyone have any more questions or asking more about this?
Hi, Aoife. This is Shirin.
Hi, Shirin.
Hi. So I have a question. So I understand that you used factorization to write the correlator in terms of the hard kernel and LCDA.
Yeah.
Can you just go to that page on top of your notes?
Yeah. Yeah, so I should have said something related to that.
So actually,
factorization.
Yeah.
Yeah.
No. So yeah. So the question was that after that you defined this twist to spectral density.
Yeah.
I did not get how one can get it. Is there a reference, or it is just a mathematical thing, or this?
This? How I derived
physical?
this?
Because what we start with, you said that this is that leading twist, yes, and then which is equal to rho T2. So is it some substitution, or there is a reference that I can...
Exactly. No, so it's just yeah, I can rewrite what I obtained. So this f pi mb squared over 2 and all that. I can express that in terms of this rho T2. So yeah, it's just a transformation of the variable u to s. I can give you the transformation. And then one obtains what you get for rho T2 as a function of what we had in the previous equation. Is it clear?
Is there a reason why it's called twist 2 then? Because this is
yeah, so I mean it's twist 2 because we only calculated the twist 2 contribution. So that
first term is leading twist, right?
Yeah, leading twist is twist 2.
Phi is leading twist.
But there's no twist 1.
So you calculate this at twist 2 basically.
Yes, yes.
Oh, okay. All right. So it's a mathematical, like a change of variable kind of.
It's just a change of variables, and I'm trying to find the change of variables for you. I think I know this. Okay. I'm referring a lot to my thesis, which I haven't looked at for about 12 years. So I'm not very familiar with finding things using. Yeah, okay, I found it. Now there's this transformation. Yeah, okay. So here we use the transformation that u equals mb squared minus q squared over s minus q squared. So we change the variable u in terms of s, okay, and then we define this rho t squared, rho t2.
Okay, okay. Thanks.
Okay. Yeah.
Yeah, thanks.
That's it.
Yeah, I was just wondering if there's something physical that I need to just.
Okay.
Okay.
Okay. Yeah, but because you mentioned this factorization theorem, I should probably mention that this is not a factorization theorem. That it's not a proven factorization theorem. It's something which we prove by order by the cancellation of divergences.
Yeah.
Okay. Okay, any more questions? Great. Okay, so let's come back to these parameterizations of the form factors, which is I think where we left off. And what I was saying was that these the form factor shape is highly affected by low-lying resonances, which are normally should be in between low-lying resonances with masses between MB minus M, let's just call it P to be simple, and MB plus MP squared. Well, I don't know, I'm doing squared because this is actually defined as T minus in the following, and this will be defined as T plus. Okay. So as I said, yeah, they're affected by low-lying resonances, and there were some pole type parameterizations. So particularly advocated in this Belle-II paper, for example. So one example of these pole type parameterizations where you write the form factor goes like some fit parameter are 1 minus Q squared over MR squared, where MR is the resonance mass, and R2 plus 1 minus Q squared over M fixed squared, something like that. Or maybe there wasn't any no-line resonance, but there was still some pole-type behavior, so we take the M fixed squared 1 plus R2 over 1 minus Q squared over M fixed squared 2, something like this. Okay, and one more thing I wanted to just mention, which I wrote later, is that in order to know what the quantum numbers of these resonances should be to affect the form factor, it's written down here for the different form factors what the quantum numbers should be of the resonances. So one has to look in the PDG. So first, one other thing is that if you're looking at a form factor that goes from that involves a BTU quark transition, then the resonance should be a BU bar state. Okay, so that's how you know what the quark content of the resonance should be. And this is how you know what the quantum numbers of the resonance should be. And if there is such a particle that exists in this range, then you know it's going to affect the shape of the form factor. Okay, so that's how we find the resonance behavior. These are the pole-type parameterizations. I mean, you could also have something simple where you don't even include the second term and see if that fits enough. Okay, but more recently, people have been using these series type parameterizations, which are quite different. Okay, so what do these look like? Okay, so I'm going to sketch the derivation of the bounds on these parameterizations, but I'm not going to be able to do it in 100% detail. So I guess in order to fully understand, you need to read yourselves afterwards. So, so the basic parameterization, we call it the series expansion. It's also called VGL parameterization. Is writing the form factor as some prefactors, which I'll explain in a minute, and then a sum over some coefficients times some variable z, which depend on t. And this z is defined as square root of t plus minus t minus the square root of t plus minus t naught over the square root of t plus minus t plus root of t plus minus t naught. Okay, so I already explained what the t plus is. The t plus is defined here. mb plus mp the whole square. Or maybe I write it here. So t plus minus equals mb plus or minus m v or p the whole square. Okay, and what is this T naught? This T naught is some just a constant which is chosen, which doesn't depend on T. Now you can derive, if you want this series to converge, you want your Z to be small. So you can derive the optimal choice of T naught in order to get the smallest Z. And this is called T naught optimal. And that's given by t plus 1 minus root 1 minus t minus over t plus. Okay, so you can probably derive that yourselves. So this is the optimal t naught to reduce z in physical range. Okay, so our Blush Refactor, so this B is called the Blush Refactor, and it's this B which gives the shape corresponding to these low-lying resonances that we were talking about. So it's defined as, for the series expansion, it's defined as Z at MR squared. And yeah, okay, that's and this phi is a complicated function, which I will explain a little bit more in a minute. It's just in order to ensure that the form factor is analytic when we impose these dispersive bounds on the form factor coefficients. So the nice thing which we will show about the series expansion is that you can impose some dispersive bounds, and then when you sum, you know that the sum over all of these coefficients should be less than 1. So that gives a bound on these coefficients, which is easily implemented. However, with these prefactors, things are a bit complicated. So the bound is simple, but the parameterization itself is a bit complicated. So there's another alternative, which is called the simplified series, or BCL. So this is void Libby, and this is really So in this case, the form factor looks like this. So we just have the pole coming from the low-lying resonance. And then we have the sum again over some different coefficients and the Z. So yeah, so this PT is just equal to 1 over 1 minus T over M squared. Okay, so this gives you an idea of what these series expansions look like. Now, what about this bound on the coefficient? How can we implement that? So as I said, I'm just going to sketch this, but I wanted to go through it a little bit so that you had some idea of where this bound comes from. Does anyone have any questions? Okay. So in order to sketch this bound, we write bound on coefficients.
Aoife?
Yeah.
Is it P, you put 1 over 1 minus T, but in the form factor you put 1 over P? Is there someone which is not the inverse there?
Ah, you're right. Thanks. Thanks, Harry. Okay, super. Thank you. Okay, so so in order to get this bound on the coefficients, in a similar way to in micron sum rules, we need to write down the correlator, which can be evaluated in 2 ways, either in the OPE or actually either on the lattice, which we've seen recently. There's some recent results, or by unitarity considerations. So let's write down this correlator. Okay, something like this. So what these J's are just quark currents. So in a similar way, instead of having some tensor, we want to work with scalars. So we apply some projection operators which project out some scalars from this tensor. So we just call these like this. So this X is just labeling the quark current. And so this pi scalar is labeled by I, which is the projector, and X by the particular quark current that we're looking at. And so this projector projects out what we want. Okay, so then we can write this thing down, this quantity down in terms of a subtractive dispersion relation. And this renders the thing finite. Okay, which is simply can be written like this in terms of the imaginary part. Okay, so now that we've defined these kinds, we can continue a bit more. And what we want to do, as I said, is to write it in terms of some hadronic representation. So that means that we can express this pi, or the imaginary part of pi, in terms of form factors. And how do we do that? Well, it's actually quite easy. So let's write down the imaginary part of this pi. So we insert in infinite sum of states. And these states are labeled gamma. Okay, so we're free to insert all of these states, and that's no problem. Now we know that in this infinite sum of states, there will be one case where, especially because of the fact that we're looking at a specific quark current, we know that gamma will contain B and PV. So let's just call L equals P, or the V, the final state to the scalar or vector meson. So gamma is going to contain VL. So that means that if we choose just the BL contribution, then we know that that's going to be less than the sum of all of the possible states, right? So we say that we just look at, we take out the sum and we just look at this place. So BL, you can say 2 pi to the 4 multiply mu minus BL BI mu 0 x BL. So it's is greater than this. Okay. And now what we have to do is that we don't want the BL here, but we want the B on one side and the L on the other side. So how do we do this? Well, we can relate these. And so that then we can write them in terms of the form factors. So we need to relate. And I will talk a bit more in a minute about how we can do this change going from the BL on one side to the BL on the other side. Because these we can write in terms of form factors. Okay, so on one side, we've written this, this correlator or the imaginary part of this scalar pi function in terms of form factors. And on the other hand, we can extract this quantity in terms of an OPE expansion. So in the OPE, we can write down this pi ix as a sum over some Wilson coefficients and some operators. So the leading order operator is 1. So it's just, you have to calculate a perturbative diagram, and then you also can compute contributions which are coming from the operator, where the operator is the gluon condensate or the quark condensate. Okay. So I don't think I really have time to go into this in more detail, but the basic idea is that, yeah, on one side you can calculate this in the OPE. On the other side, you extract, assuming that the function is analytic, you can relate the BL in the final state to the transition element from the B to the L, and that you can write in terms of form factors. Then inserting for these form factors this series expansion here in this form, it's possible to get a bound on the sum of the coefficients, the square of the sum of the coefficients. So in order to look at this in more detail, I invite you to read these papers, which I'll write in the notes. I'll give the numbers, or this one. Okay. Okay, does someone have questions? I know it was a very sketchy explanation, but it was better than nothing. Okay, good. So yeah, no, the other thing I want to say is that other than calculating these things in the OPE, more recently, people have been calculating these, what we call susceptibilities, on the lattice. And then one gets direct lattice results, which will provide a bound on the coefficients, which is very nice. So the only problem with this series and simplified series parameterizations is that often the bound which you impose on the coefficients is not really very constraining. So particularly for B to very light states, it turns out that your Z is small and the series converges very well, and the bound that you can actually impose on the alphas is not really useful to constrain the form factors. So then you might want to find ways in order to saturate the bound by maybe combining different channels. But yeah, so really what you need then in that case is to have information in the low QSquare region from light chromosomes and in the high QSquare region from lattice, and then your parameterization of the form factor does not actually matter all that much. So the problem arises when you don't have information either in the low QSquare and the high QSquare region, and that arises in various cases. Or just if the lattice people don't want to use the light chromosome results at low QSquare. But yeah, for these heavy to light decays, it's difficult to actually get really useful information from imposing this bound. Okay, so we've talked about the form factors, we've talked about the Wilson coefficients. But we haven't yet talked about how this is all put together. So one can give the example of the beta K star decay. So as I said, for semi-leptonic decays, we only need the form factor. But when we're looking at other decays, so B2 non-leptonic, so we have say 2 mesons in the final state, or if we're looking at beta S gamma or beta S LL, then just the form factor is not enough. Okay, then why is that? So let's have a little look at the case of beta K star error, because it's something that a lot of people are interested in. So we can calculate the full result in this framework called Pcb Factorization. Okay, so we can write the matrix element in terms of some form factor times some Wilson coefficient or some coefficient plus a convolution between the B meson Lycan distribution amplitude, again this hard kernel that we mentioned before, and the Lycan distribution amplitude for the K star, and then some higher order terms. So at leading order, what kind of diagrams contribute? So you have, imagine you have your B meson with your B4 and your D bar. So your spectator just goes through for now, and we could have the C7, the O7 operator, which gives off a virtual photon, and the S4. And then this virtual photon goes into an alpha resonance. So here we have C7 or O7, let's say. So remember, we looked at the operators yesterday, and I showed you the list. And so this O7 was the operator containing the photon, the beta S in the photon. Right. So that's the first easiest. Of course, it's also the contribution from O9 O10, but that's just really trivial. So we don't even need to write it down because it's exactly this. O9 10. Because it's the operator that contains the BS and the alpha segments. Okay, what other leading contributions do we have? Well, we have another one, which is the source of a lot of problems, which looks like this. And for example, you can emit the photon then from different places, but for example, we could emit it from here. So yeah, for example, we could emit it from here, and then it goes into a plus and minus. And here we have a quark loop. And then finally, at leading order, the other thing one can have is and again, we emit a photon which goes to electrons. And this photon could be emitted there, here, here, or here. So this topology is called recanalization. Okay, so these are all the leading order contributions to beta alpha plus and minus in this framework. So you have 07, 09, 010. These are these 4 quark operators that we looked at, 01 to 06. And this is also, I think it's 03 to 06. Does anyone have any questions about this? Okay, so one thing to point out is that these 3 diagrams are all described in terms of, like the non-perturbative part is all described in terms of the form factor. As you see, the spectator quark doesn't take part, so they can all be described in terms of a form factor and in terms of some coefficient that we calculate in terms of the Wilson coefficients. However, this one is a bit more complicated and it cannot be described in terms of form factor. And so we need to use the second term to calculate. Now, it turns out that because of the CKM elements, this recanalization, and because of the small size of the Wilson coefficients, this term is actually highly suppressed for beta k star LL, and so it's normally not taken into account at Libby. So then, we go to the next order. So okay, so there's one more thing that I should say, that here this quark loop contributes. And the quark loop can be calculated, of course, perturbatively, and it's no problem. However, there's the case where the Q squared of the photon lies close to, so in certain ranges of this Q square, you can calculate the quark loop perturbatively, and maybe the result is quite accurate. But once this Q squared goes somewhere near the resonances or above the resonances, then factorization breaks down, and our perturbative calculation is not really accurate enough. And so at first, people thought that if we cut out the phase space of Q squared around the charmonium resonances, then that would be enough in order to get, like, if we took our calculation from in the range Q square 1 to 6, then it should be accurate and not affected by these resonances, and factorization should work. But then when there were the B-physics anomalies, and when people started to get discrepancy between theory and experiment in this very channel, people started to wonder if these resonances are maybe affecting more of a region of Q squared than we thought. So then people started looking into these resonances in quite some detail and trying estimating their effect. Yeah, so you can ask me more about that later if you're interested. Okay, so now let's have a look at how one calculates then beyond this leading order. So the diagrams that you need to calculate if you want to go to corrections in Alpha S are going to be like this. So there's calculation, there's diagrams where you still only have the where the spectator is not affected and stays just goes right through. And there's some diagrams where you get some hard scattering between the when the spectator quark has a hard gluon that couples to it. So the ones where it's not affected, you could have something like this. So remember that this O8 operator was B to S gluon. So if the gluon goes back and couples to the B quark line, then you could emit a photon either here or here or here. So for example, here, and then you have your alpha elements. So the other option is that you have these 1 to 6 4 quark operators. So again, you get this loop. And the spectator is happily going through. And then you have a gluonic correction, either like this, or like this, or like this, sorry. And then you could have your photon emitted anywhere from here, from this loop. Okay, so these are called the form factor corrections at order alpha S. And then finally, you have the case, as I said, where the spectator is involved. So for example, you could have this O8 operator where you have a gluon attached to this spectator leg. And then again, you have in any of these positions, you could have a photon emitted. And finally, you have the case where you have the O1 to 6 operators. Then you have a gluon, which is coupled to the spectator. And again, you can have a photon emitted from any of these points. Okay, so in order to get the alpha S corrections, we need to calculate all these diagrams. And then you get corrections both to this CA, so the form factor coefficient, and to this TA, this hard kernel. So for these ones, you're forced to calculate the result in terms of this B meson distribution function and the final state light cone distribution amplitude. And that is a problem because actually for these B meson distribution amplitudes, we don't have loads and loads of information about their nature, even for the final state, like in distribution amplitude. So that would be a priority to try and learn more about these functions, because that would help us be able to estimate these sorts of corrections much better. So 5B and 5P squared. Not very well. So the lattice could tell us more about this, and there are some lattice groups working on the pi LCDA, maybe and the K. The K stone, the lattice is more complicated. need more information. For the phi b, hopefully at Belle II, we might get some information on this quantity. And how we can get information on this quantity is by looking at B to gamma L nu decays. So you have your P meson. Here you have the W, which goes to your Lu. And here you emit a photon. And by studying the decay rate for this process, hopefully we're going to get information about phi b. And so this could be really interesting. We already have a lower bound, so the first moment of this B meson distribution amplitude is called lambda b. First moment of phi b. And we know that it should be greater than 238 MeV. But that's all that's known. So hopefully Belle II might give us some interesting information about this. Okay, I think that's all I have to say for today. I know we have the tutorial later, so you can ask me even more questions then, because I'll be there. But maybe some people have questions right now.
Actually, I won't be in the tutorial this afternoon,
Yeah.
so maybe I can ask a question.
Sure.
But with this last process, you're right, it's very interesting, and I hope Belle II will make a measurement. But this the chances that it's not an internal photon but coming from the lepton in the final state, how does that?
Oh no, that's I mean, we can calculate that very easily. So that's added into the.
And you subtract it off. Okay, including in say, I guess it's an easy process. So
Yeah.
it doesn't mess things up too much than in.
No.
Okay.
No. Yeah. No, it's a good question. Yeah, I just wrote down this diagram because it's the one that it gives the interesting part. But yeah, the photon, the lepton can also emit a photon, and this is taken into account. Yeah. But the case where the photon is emitted from the B is suppressed, but also taken into account.
Okay. Just one other question on this. Been thinking about this measurement for BESS 3 and to do it in D decays. I presume the interest is also there in measuring this, right?
What this the same D to gamma L nu.
D to gamma L nu, yeah, because we can.
I'm actually working on that.
Okay. Yeah, because there are.
So maybe we can talk about that.
Yeah, there are some people working on it, and it's again an interesting thing. Okay, we'll take that offline. So that's good. Okay. All right, Aoife. So as I apologize, I have some administrative work at the Institute this afternoon, so I will not be there in your tutorial, but Namit will be there.
Okay, great. Super.
So everyone else will see you then. Okay.
Yeah, see you then. Okay, bye. Thanks
Bye-bye.
a lot.
Bye.
Bye.